Hello, in this video, we're going to be looking at the first part of lesson 9.6, which is on geometric probabilities. The essential question that we'll answer in both day 1 and day 2 is how do you calculate geometric probabilities? Before we get to calculating geometric probabilities, it's important that we have some vocab words to describe them. So first off, a sample space is the set of all possible outcomes of an experiment. So for example, if my experiment was, I'm going to roll a standard die, the sample space would be the numbers 1 through 6, because when we roll a standard die, we always land on the number 1, 2, 3, 4, 5, or 6. Now, an event is any set of outcomes in a probability experiment. So maybe I say, what is the probability that you roll a 2 on the dice? Well, that's an event out of the sample space. Geometric probability is a specific type of probability. The probability of an event is determined by a ratio of geometric outcomes, such as lengths, areas, or volumes. And the two that we're going to work with in this section are lengths and areas. We'll learn about volume in our next unit. One important thing to note, and it's already starred here, I'm going to highlight it as well, is geometric probability is used when an experiment has an infinite number of outcomes. So the dice example I gave at the beginning, where you roll a dice, that wouldn't be geometric probability. That's just basic probability. For geometric probability, we're going to look at 3 different models. You have a length model, an angle measure model, and an area model. For the length, you might have a sample space, for example, being all the points on AD, and the event would be that I randomly pick a point on BC. The probability that my random point is on BC is equal to the length of BC divided by the length of AD. We can also use angle measures to determine geometric probability. For example, we know that a circle is 360 degrees. So the sample space would be all the points on the circle, and then an event might be something like the shaded region. So for that shaded region, we take the measure of the angle divided by the total degrees, which is 360. Just like on this one, we divided by the total number of points possible, A through D. And then the last one here, the area model. This is a model that we used a little bit in 9.3. You might have a sample space where it's all the points on the rectangle, and then we might randomly choose a point, and our event might be all my points are in the triangle. So if I wanted to know that the probability that if I randomly pick a point, it's in the triangle, I would need to calculate the area of the triangle and then divide that by the area of the entire rectangle, which would be the sample space. For our examples today, we're going to start off with a length model, then move to angle measure, and then we'll end with area. Let's start an example using length to find geometric probabilities. A point is chosen randomly on segment AD, and we want to find the probability of each event. Notice that AD here is the full segment all the way from the left to the right. So we need to start by figuring out the length of AD, and we can do that by adding the sections together. 4 plus 3 plus 5 adds to 12. So the length of AD is 12. To find the probability that our randomly selected point is on segment AC, what we need to do is we need to take the length of AC, which is from here to there, divided by the total sample space, because the point can be anywhere on AD, so the sample space AD will be our denominator. Now, if we just sub these values in, notice that AC is 4 plus 3, so 7. And AD is 12. So our probability as a fraction is 7 over 12. You can also express that as a decimal. Take your calculator and do 7 divided by 12. And when you do that, you're going to get this number, 0.58333 and then it just continues to repeat. If we write it as a decimal, we just need to round to the hundredth, so that's 0.58. If I want to write it as a percentage, you can move the decimal over 2 places or take that value right here and times by 100. And now I can get a little bit more accurate here, so I'll say 58.33%. So all of these are the same answer, they're just different ways to express it. Probabilities can be either fractions, decimals, or percentages. Next up, we want to find the probability that the point is not on AB. And if I look at my picture here, AB is 4. So not on AB is going to be the rest of the sample space. 12 minus 4 is 8. So for my answer here, not AB divided by the sample space AD, we would have 8 over 12. You can reduce that to 2 over 3 if you divide by 4. As a decimal, you're going to see 0.66666, etc. So we'll go 0.67. And then as a percentage, we can multiply that by 100 or just move the decimal 2 positions that way. And that would be 66 point and then 67%. So that is your solution expressed 3 different ways: fractions, decimals, and percentages. Go ahead and try the try now on your own using the same diagram. Please pause your video now. Here's your solution to the try now. It can be in either AB or CD, so you want to add those lengths together. 4 plus 5 is 9, and 9 over 12 is 3/4, 0.75, or exactly 75%. Now let's try a real-world application of the length model. Suppose that a stoplight has the following cycle: green for 25 seconds, yellow for 5 seconds, and red for 30 seconds. Let's draw this out like a segment length. So we have the first 25 seconds, the light is green. Then it's yellow for a little bit, 5 seconds yellow, and then it's red for 30 seconds. So the full cycle of the light is just going to be the sum of those values. So take 25 plus 5 plus 30, and that is 60 seconds. So now we have everything we need to answer these questions. What's the probability that the light will be yellow when you arrive? To find the probability that the light is yellow, we need to take the length of yellow divided by the length of the total cycle. So the yellow is 5, the total cycle is 60. And then let's express that as a fraction, decimal, and percent. You can use your math fraction or N over D buttons to help you with the reducing. That's going to make 1/12. On my calculator, it's 0.083333. So that would be 0.08. And then if I do a percent, I just multiply by 100 or move the decimal over, and that would be 8.33. So that is the answer expressed 3 different ways. Next up, let's look at the probability that the light will not be red when you arrive. So probability that it's not red divided by the total cycle. Well, it's only red for 30 seconds, and it's a 60-second cycle. So if I take 60, my total, and then I subtract how many seconds of that are red, we have 30 seconds in which the light is not red. So let's take that value, 30, divide it by the total, 60, and you can see that reduces just a half. So 1/2, as a decimal, that's exactly 0.5, or 50%. Here's a quick try now for you to try on your own. I'm going to help you set up the picture on this one, and then I'll let you finish solving it on your own. So a light rail arrives at a station once every 15 minutes. So let's say here's time 0, they arrive in 15 minutes, then they arrive in another 15 minutes, so 30 minutes from where we started. And Every 15 minutes, the light rail arrives and waits at the station. So here, let's just assume like the light rail stopped. They wait at the station for 2.5 minutes, and then they get on their way again before they get to the next stop, and then wait there another 2.5 minutes, and then they finish up. So the 15 is actually the length of the full cycle. Just of that 15 minutes, 2.5 of them, the bus is there, and the rest of the minutes, the light rail bus is not there. So let's find the probability that the light rail will be at the station when you arrive. It's a 15-minute cycle. Every 15 minutes, the bus arrives at the station, or the light rail arrives at the station. And then of those 15-minute cycles, only 2.5 minutes are when it's actually stopped and waiting. When we simplify this, the 0.5 makes it difficult. So I'm just going to double everything to clear that 0.5. And that's 5 over 30. And now you can divide by 5, simplify your fraction, and we'll have 1 over 6 as a decimal. The number that the calculator gives us for 1 over 6 is 0.16666. So as a decimal, I'd have 0.17. And then as a percentage rounded to the nearest hundredth, we would move the decimal over 2. So that would be 16.67. So all three of these are the same answer, just expressed different ways. Fractions, decimals, and percentages. Now we're ready to move on to the next model. We did some segment length models for example 1, example 2. Now in example 3, we're going to use some angle measures to find geometric probability. We have a spinner here that's a circle, and we're going to use that spinner to answer these questions. What's the probability that the spinner lands in the 135 degree section? So that is right here. 135 degree section is 135 degrees out of my total sample space. The full circle is 360. So now we just need to reduce the fraction, and you have a fraction button on your calculator. If you have a graphing calculator, you type 135 divided by 360, click math, and then pick the first choice fraction and hit enter again, and it'll reduce it for you. If you have a TI-30 scientific calculator, or if you're borrowing one of the yellow calculators, on the TI-30 scientifics, there's an N over D button that will reduce the fractions for you. Here in this problem, if I do it by hand, I could also just, try to find the number that works by hand. Dividing by 5, I think, is kind of where I started, 27 over 72. And then I could divide, I noticed those are both divisible by 9, so I have 3 over 8. So 3 over 8 is the fraction. Let's also do a decimal and percent. 3 divided by 8 is 0.375. And then to make that into a percent, we just slide the decimal over 2 positions. So that is 37.5%. So all three of these are different ways to express the same probability. Next, let's look at the pointer landing in a 90 or 75 section. This means that it can be in either. So it could land in the 90 section, or it could land in the 75 section. So we need to put those together. So let's take 90 plus 75, and then we'll divide it by the total number of degrees in the circle, 360. We add that together, we get 165 over 360. And then you can use the math fraction button or the N over D button to simplify your fraction, and it ends up being 11 over 24. Now, as a decimal, what the calculator gives us is 0.45833, repeating. So rounding to the hundredths, as a decimal, it would be 0.46. And then if we want to do the percentage, The decimal is over twice times 100, and then it would be 45.83%. Go ahead and try the try now problem there on your own. Please pause your video. I'm going to stop this video right here and we'll go over the final example, which is the area model, in another video for 9.6 day 2. Thanks for watching. Bye.